Are you familiar with the term nuclear medicine? Nuclear medicines employ radioactive isotopes such as technetium-99, iodine-125, etc. for diagnosis and treatment of diseases. Here my question is, how will you determine the length of time of this radioactive element that can be stored for its radioactivity to decay to a safe level? In order to calculate this time period, you may use the integrated rate equations. Integrated rate equations can be used to estimate the time required for a reaction to proceed to a certain extent. Let us discuss this in detail. Consider a reaction where reactants R gives product P. The differential rate equation for this reaction may be written as minus dR by dt equal to K into R raised to N. K is the rate constant and N is the order of the reaction. If the reaction were of zero order, then the value of N would be 0. In this case, you may write the differential equation as minus dR by dt equal to K. Let it be equation number 1. Rearranging and integrating, you will get the equation as R equal to minus KT plus I, where I is the constant of integration. Next, we will find the value for I. For that, consider the concentration of the reactant at time t equal to 0, the initial concentration as R0. Substitute this information in the equation number 2, that is R0 equal to minus K into 0 plus I. Now you will get the value of I as R0. Substituting this value of I in equation number 2, you will get the equation number 3, that is R equal to minus KT plus R0. You can see this equation is in the form of y equal to mx plus c. Thus, if you plot concentration versus time, you will get a straight line with the equation R equal to minus KT plus R0. The negative slope of this graph gives the value of the rate constant and intercept gives the initial concentration, which is R0. In general, for all zero order reactions, say for example, photochemical reactions, photosynthesis, you will obtain a graph exactly like this. Next, we will see the integrated rate equation for first order reactions. For example, a reaction R gives P. Here, the differential equation takes the form minus dR by dt equal to K into R. Rearranging and integrating this equation, you will get ln R equal to minus KT plus I. Let it be equation number 5. Now, you may find the value of constant of integration as done earlier. Consider the initial concentration R0 at time t equal to 0. Using this information, in equation number 5, you will get the value of I as ln R0. Next, you may substitute the value of I, which you have got, into equation number 5 to get the integrated form of the first order reaction as ln R equal to minus KT plus ln R0. This equation also takes the form y equal to mx plus c. Hence, a plot of ln R versus time gives a straight line whose slope gives the rate constant. The y-intercept of the graph gives the value ln R0. Next, we will see another representation of integrated rate law of first order reaction. The integrated rate law of first order reaction may be rearranged and converted to log to base 10. Then the first order reaction can be written in the form log R0 divided by R equal to KT divided by 2.303. Let it be equation number 8. Based on equation number 8, if you plot a graph between log R0 by R versus time, you will get the value of slope as K by 2.303. Next, let us consider a gas phase reaction of order 1. Initially at time t equal to 0, the pressure of AB, Pi. When reaction proceeds, that is, at time equal to T, the pressure of A decreases. Let the decrease in pressure of A be X atmospheric pressure. Obviously, the increase in pressure of B and C also will be X atmospheric pressure each. Now, the total pressure PT is given by the sum of pressures of reactant A and products B and C, as you can see here. P total equal to Pi plus X. Next, write the final pressure of A in terms of initial and total pressures. Then, PA equal to 2Pi minus PT. Substituting these data, you will get the rate constant as K equal to 2.303 by T log Pi divided by 2Pi minus PT. Next, we will discuss half-life of a reaction. The half-life, T half, of a reaction is the time required for a concentration of a reactant to get reduced to 1/2 of its initial concentration. That is, the time required for R to become R0 by 2. Substituting this information in equation number 4, you may get half-life of a zero-order reaction as T half equal to R0 divided by 2K, where K is the rate constant. Similarly, you may find the half-life of a first-order reaction. Consider equation number 7. When R becomes R0 by 2, then T becomes T half. Substituting this data, you may deduce the equation T half equal to 0.693 divided by K for a first-order reaction. Now answer me, have you heard of radiocarbon dating? Well, radiocarbon dating refers to the method of determining the age of an object containing organic material using the properties of radioactive carbon-14 present in it. How will you determine the age of a tree using the properties of radioactive carbon-14 in it? I can give you a hint. All radioactive disintegrations are of first order and half-life of the carbon is 5760 years. Also, we realize that we can relate the concentrations of reactants and time using integrated rate law. Think about it. With this, we will summarize the video.
Manorama Horizon. Learning made simple.